Okay, good. Good. So I appreciate that I've just kind of given you this as a method, as a recipe, if you like. Okay? Without really dwelling on why it works, girls. Without really dwelling on why it works. And I kind of came up with an intuitive, well, I didn't come up with it, but I kind of saw an intuitive way for why it works. And it was using this idea of areas. Okay? Because I've introduced this idea that x squared, the reason why we say x squared rather than x to the power of 2 is because we're literally talking about the square. Namely, the area of a square with side length x. Okay? That's where my x squared is represented geometrically, represented visually. Okay? 12x, what would that be? Visually?
X is the width.
Exactly, so it's the same width as this. I know it's not drawn accurately, but it is the same width as this. And where's the 12?
The height.
Okay, good. So 12 is from there to there. Okay? Now, the 3. Now, notice I'm using this. This is where it comes from. Okay? If I set this equal to 0, would you be happy I could equally write this as x squared plus 12x equals 3?
Yeah.
That would equally work. Okay? And the reason why I want to write it like that is because I really want to isolate the two terms that I care about. These two, the terms with the x in. Okay? Do you remember all of these things I just said always look at the first two terms. That's all you need. You don't care about the last one. It just comes along for the right. Okay? So I've just isolated it on the right hand side. Okay? Hence I've just made it equal to 3. And if I want to represent that as an area, I don't care what that shape is. It's just an area. Right? So, what did I do then? So how did I get from here to here? What did I do to
We divide into shapes, shapes we can use.
So just talking about it algebraically, how did I get from 12x, so x squared plus 12x, into x plus 6 all squared? What did I do to this 12?
Break it down.
Exactly, I halve it, right? I halve it. So if you think about this, well, I clearly want to hang on to this x, because you can kind of see those two things match up. So if I halve it, surely all I should do then is chop it in half, right? In which case, this height here is going to be 6. And this height here is going to be 6. You okay with that? Yeah? Alright, fine. Well, this is still x. This is still x along here as well. So really what I've got now are two separate shapes. A 6x and a 6x. Well, if I join one of those onto here, would you be happy I get something that looks like this? So there's my x squared. Okay? If I join the bottom bit onto here, would you be happy I get this? Yeah? That's my 6x. This bottom bit on here. Imagine these are two separate shapes now. Okay? And then this one, all I'm going to do is rotate it through 90 degrees. And hence I'm going to stick him on there. Does that make sense? Right? And then on the right hand side, all of this is just equal to some random shape. I don't care what that is. Okay, but you can kind of see that they're roughly the same thing. It's just got an area of 3. That's all. Now, hopefully you can see now why it's called completing the square. Because what would I have to do to this to make it a perfect square, to make it a complete square? What's missing?
This one.
This bit down there. And what's that bit worth?
6 times 6.
Yeah, the 36, right? And the same thing here, if I wanted to complete it, I've got to stick it there as well. So in order to complete the square, I need to consider this 36 term here. Is that okay? So the reason why it's called completing the square is because I'm literally completing the square. Because of course the area of this thing now will just be equal to what? X plus 6 all squared, right? That's the area of this thing. That's then going to be equal to, well, this green bit was 3. It was worth 3 before. That's literally what I said. But when I add it on to 36, would you be happy I get 39? And if I bring it all back over on the same side, I get x plus 6 all squared. Take away 39. Equals 0, but actually I just wanted to make it look like that. Okay. So when I say complete the square, it's not a coincidence. I am literally completing the square. Because I have to add on this bit in order to make it a complete square. Is that okay? Don't worry if you don't understand that. I just wanted to show you the reason why it's called completing the square. Okay, good. Alright, fine. Let's continue with this then. Let's continue. continue with this idea. What if I gave you something that looks slightly different? So what if I gave you something like this? What if I gave you something like that? And I asked you to complete the square on this. How would I do that?
Divide by 2.
Okay, divide by 2. Why would I divide by 2?
Because both the x squared and x have a number that can be divided by 2.
Good, so first things first, you're saying these are the only two terms that I care about when I'm completing the square. That's literally what we were just doing, right? Those are the only two terms I care about. And the thing which is making this awkward is it is a, can you remember the name of this? When it's not a monic quadratic?
Non-Monic.
Non-Monic quadratic, okay? I go, okay, this is totally fine, I can just pull a 2 out. That's fine. So if I pull a 2 out, I get 2 lots of, minus 3 just falls down. What do I get inside the brackets then? Perfect. All I have done is just factorised a 2 out. Okay? And then it's just basically a case of, well, let's just pretend that I gave you this. Let's just pretend that I gave you x squared plus 2x and asked you to complete the square on this. What would that be?
X plus 1 squared. Plus 1. Wait, I forgot.
It's minus 1, right?
Minus 1, yeah.
Yeah, because if I expand that out, I get x squared plus 2x plus 1. I don't want the plus 1, so I've got to take it away.
Yeah.
Is that okay? Yeah. So that's what goes inside the brackets. Yeah? So I get 2 lots of this thing. Right? And that could theoretically be your final answer. But we're better than this. How could you tidy this up? I don't really like the fact that I've got 2 being multiplied by a set of brackets and a number. So all I'm going to do is multiply this 2 through everything inside the brackets. Okay? So I'm going to say it's 2 times by this thing, the x plus 1 all squared. Okay? And then 2 times by negative 1, which is...
Negative 2, so it's negative 5.
Perfect. I've still got the negative 3 there, so you're dead right. It'll be this. Okay? So you see, that is no harder than what I was doing before. It's just you have to do an extra couple of steps to pad it out. Okay, but it's exactly the same principle. Right? Incidentally, where would the vertex of this parabola be? Where would the vertex of this parabola be? Remember, the vertex is just a turning point.
5? No, wait.
So let's think about the sequence of transformations that have happened here. What would you start with? It'll be the x plus 1 first. What does that do? It shifts it to the left by 1, right? Yeah? Then what would you do next? The times 2 or the take away 5?
Times?
I do the times in by 2. What does that do?
First.
What does that do?
It becomes wider, I think, or narrower.
It becomes narrower. It's basically somebody grabs hold of your graph and pulls it up in that direction by 2.
Narrower.
So it becomes narrower. Has that affected the vertex?
I don't think so.
No, absolutely. So at the moment our vertex is sitting at negative 1, 0, right? So timesing by 2 just makes it narrower. It doesn't affect where the vertex is. So what's negative 5 doing?
Shifting to the... yeah, shifting down.
Shifting down by 5, right? So where's my vertex going to be? Negative 1, negative 5. Yeah, good. Does that make sense?
Mhm.
Yeah? So don't worry about the fact there's a 2 there. It's exactly the same thing as what you're doing before. Yeah? Good, excellent. Has everyone finished with that thing on the right hand side? Can I rub it off? Okay. In which case then, could you have a go at this one here for me? Let's try 3x squared plus 18x plus 2.